Yeah, today we'll go over the module 17 lipids, and we'll start with the lipid definition and function. Lipids are organic compounds that have one similar or common physical property, that they are not soluble in polar solvents such as water or alcohol, but they are soluble in non-polar solvents such as cyclohexane, hexane. So the idea of lipids, those are different organic compounds not soluble in polar solvent, but they are soluble in non-polar solvent. And their function is very important in our human body as well animal body. They are storing energy. They are very crucial for the structure of many cells in humans and animals. They're used to protect and insulate cells within a human body and animal's body. They are used to produce mRNA, which is abbreviation for message ribonucleic acid, from the DNA after transcription, after copying it from the DNA. And part of the lipids called steroid lipids, steroids hormones, as we will see, and they are very crucial in our life, in human body, So now let's go and look at the types of lipids. There are two types, or major two classes or categories of lipids: lipids based on fatty acids and lipids based on steroids. So before we go further, we have to look at the fatty acid. What do we mean by fatty acid? Fatty acid is nothing less than just a normal carboxylic acid, but this time we speak about long chain 22 carbon or more, to start from 4 to 22, or can go more than 22 carbon atom within the chain itself. And the chain itself, as you can see here, this is the chain itself. This is called the long chain. This is non-polar part, correct? And the carboxylate ion, that's a polar part. The polar part here is given the classification as a head, and the long chain as a tail. So we have a head and tail. So this is a head, and this is the tail. So we have a head and tail. So the fatty acid, they have a head, which is polar part, small, tiny, but the long one is the long chain has a higher molar mass, as you can see with the structure here, and that's non-polar. So we have head and tail. The fatty acid can have three types. Let's go out and look at the type. The first we have seen here, this is saturated fatty acids. The unique about these saturated fatty acids, you don't have any double bond at all. So all the bonds are single bonded. So you have 22 carbon atoms or more connected in a single bond. So this is saturated fatty acids. There are other types as well. We have monounsaturated fatty acid. Monounsaturated means they have only one single bond. And we have polyunsaturated fatty acid. They have plenty of double bonds. Like here we have, this is our head, polar. This is our tail, and this is our double bond. This is our double bond. This is unsaturation, and this is polyunsaturation, because we have two double bonds in these fatty acids. This is just an example of the three types to put together, or the two types, not three types, sorry. The two types, which is here, is just show you saturated one. All this here single bonded, all of it single bonded up to here. And this is our head, and this is the rest is our tail. So And the unsaturated, the monounsaturated, mono means one single, this is one single, one double bond. The rest of the molecule is single bond. Because we have one single double bond, this is one double bond only, so we can have isomers. We have cis and trans isomers. You can see this is unsaturated linoleic acid in cis form. This is the same linoleic acid in trans form. So you see here, this H is opposite to this H, and the groups, this one here is opposite to this group. This is a trans. The unique about those two unsaturated, monounsaturated fatty acids, this one here, it has a knick. So it go up, see, up here, and then goes down like this. So it has, we call it knick. A knick here will lead, the knick here will lead to instability because this molecule cannot stack each other in layers. This one just straight double bond, straight chain. There's no problem with the trans. You see the trans is straight. There's no knick there, like going up and down. So it goes, if I want to just make it here, see here, just one chain, no knick. Here it goes up and then goes down. So the unsaturated linoleic acid, the cis, is less stable because of this knick, and the trans linoleic acid is more stable because they can stagger itself in layers, one layer after one layer after one layer. This stacking here will lead to higher, stability and higher melting and buoyant, while the cis does not have this property. Okay, so that's just explain the whole thing here, and this is what we have explained in a couple minutes about the trans has higher stability because it can stagger layers after layers because they don't have this problem with the nick in the cis form. So the lipids based on the fatty acids can be divided in 4 classes. Waxes, okay, so this is waxes, triacylglycerol, glycerophospholipids, and sphingolipids. So we have how many? We have 4 types of fatty acids that the lipids will be based on them. So those categories based on the fatty acids, again, let me repeat myself: waxes, triacylglycerol, glycerophospholipids, and the sphingolipids. Let's go and look at each one in some details. So if you look at waxes, what are those waxes? Waxes, they are lipids. They are not soluble in H2O or in a polar solvent, but they are soluble in non-polar solvent. And if you look at them very closely here, they are made of one fatty acid. This is a fatty acid, and this is a long chain alcohol. And as you have learned before, if you add alcohol with the acid, you get an ester and water, correct? So now this ester here is, not here, this ester here it is, that's an ester called wax. So wax are really is esters of one fatty acid connected to a long chain alcohol. So this is one part of lipids, correct? So that's the part 1 based on fatty acid. We have a fatty acid there, reacted with the long chain alcohol. The second one, triacylglycerol. Now, this one here, you will see that this here is, this is a glycerol here, correct? Glycerol has 3 hydroxy groups, correct? 3 hydroxy groups, and this again, an ester again. And this one here is carboxylic acid, saturated. This is unsaturated, monounsaturated fatty acids. And this is polyunsaturated fatty acids. So it has too many. Here it has how many? 1, 2, 3. 3 double bonds. Here has only 1, which can be cis or trans. And here has none. The top has none. So those are 3 fatty acids with different types, are connected to the glycerol. And this type of lipid is called triacylglycerol, which is really based on the fatty acid connected to one glycerol. Glycerol is an alcohol with trihydroxy alcohol. So it's an alcohol, but as I said, it's connected to 3 different fatty acids, and you make another lipid called triacylglycerol, which is fatty acid based. Correct? Number 3 is glycerophospholipids. Remember here, we are still using what? Glycerol and fatty acid 1 and fatty acid 2, correct? Now the problem here, we have replaced, if you go up to the triacylglycerol, we have 3 here, correct? So if you look at this, we have 1, 2, 3. So we have 3 fatty acids. We replace one of them with what? We will replace them with phosphate group and with the amino alcohol group. So we'll replace one of the fatty acids. So we are replacing the 3rd fatty acid with what? With the phosphate group and the amino alcohol group. So with amino alcohol. So now we have to speak about glycerophospholipids. Phospho here, this phospho here, because we are using the phosphate, correct? So they are very similar to this. Instead of 3 fatty acids, that will be glyceryl lipid, correct? That's the top. Triacylglycerol, correct? Triacylglycerol. We have glycerophospholipids. We are replacing the 3rd fatty acid with phosphate and amino alcohol, correct? So amino alcohol, this called, also you'll see it has a specific name, choline, called choline. So now, if you look at the phospholipids, go back and phospholipids. Now you have very unique thing that you have. This is polar here. Here it is. This is polar. And let me see here if I can draw it. Here is polar. All this here non-polar, and this one is connected because it's the OH is connected to the fatty acid and this. So this part is non-polar. So you have 2 polar parts, which one this phospholipids can come together and make 2 layers. We call it bilayer. So you can make bilayer. You can see how nice this is. Let me just blow it up for you here, guys. Yeah, I'll just show you here the bilayer. I'll go back to the original size. So this phospholipids can aggregate themselves into 2 types. Planar bilayer, those within the human cell. Within the human cell, the bilayers are really protecting the nucleus inside the cell. So this is the bilayer here, and you will see all this polar. The blue one at the top, the heads are polar, and dangling down here, all this down here are the long chain. And here is the polar part, and dangling up the, what we said, the non-polar long chain. And outside is aqueous. Outside the cell is aqueous. Here is water. So this is one type the phospholipids can form, and this is bilayer is very important for the cell to protect the nucleus. Inside the nucleus there are genes, there are DNA, and the transcription of mRNA, you can see you need something that protect the nucleus of the cell, correct? And this is the phospholipids is there as a protecting function, correct? And sometimes the phospholipids can arrange themselves in micelles. See how nice? The H2O is inside, correct, as here, and the H2O is outside too. And you will see why, because all this here, the heads are polar, and the heads are here, the same thing are polar, and the chain is just dangling there, dangling up and down. So the long chain there, but the blue heads are those the polar side. So this is phospholipids are very, very important. Let me go down with the size now, normal size. Yes, so there are two possibilities for phospholipids. They can aggregate themselves, coming together and make bilayer, protect the inside the cell, the genes, the DNA, the mRNA. So, or they can go as a micelles and can carry a lot of other stuff unwanted in and out the liver, or in and out any other section of the body where the lipids can be stored. Okay, so this aggregate structures both of this micelle type and the bilayer type called liposomes. So they have a unique name called liposomes. So let's go and look at the fourth type of the lipids based on fatty acids. We have sphingolipids. So we have, if you can put this one here, this is sphingol, and then lipids. Sphingolipids is based on sphingosine. This is our sphingosine here. I hope I can. Let me throw. This is sphingosine connected to a hydrocarbon chain, and then our fatty acid has to be there. Okay, because they have to be based on fatty acid. So one fatty acid is there, and the phosphate, like the phospholipids, and the amino alcohol, choline is there. So they are very familiar with the phospholipids, but the phospholipids does have what? Does have a glycerol, but this one does not have a glycerol, missing a glycerol. And the phospholipids has two fatty acids, and one phosphate and one choline or amino alcohol. Here we don't have any at all to do with glycerol. We have sphingosine connected to hydrocarbon chain. Okay, and you can see the sphingosine here. This is your what? Your sphingosine. Here it is. This is your sphingosine. This is your phosphate, and this is your amino alcohol, correct? And this is your hydrocarbon, sorry. This is your hydrocarbon, correct? The long hydrocarbon. And there is fatty acids. Let me see. Yeah, one is the sphingosine, and this is, yeah, this is a fatty acids. This is a fatty acid. So you can see how the whole thing is developed on this. So you have 1, 2, 3, 4 connected to this sphingosine A in the A position. So, but they don't have a glycerol one. Sphingosine structure can be given here. You can see that's the long sphingosine structure here, connected. Here it is. Excuse me. Now let's look at this the fatty at lipids based on not fatty acids but lipids based on steroids. Well, it turns out to be steroids. They have a steroid skeleton or nucleus made of 4 Here it is. Those are 4 fused cyclic rings. 3 of those 4 here, if you look at this, 3 of them are 6-member ring, and 1 of them is 5-member ring. So 3 of them 6-member ring, and 1 of them is 5-member ring. So this here, this is called the nucleus of the steroids, or steroid skeleton. So all the steroids, anytime I say steroids, they have to have this nucleus, or this basic unit, or this basic formula there. This is a nucleus or steroid skeleton. We have to have it in order to say a steroid. Otherwise, the molecule is not steroid. Some of those steroids, as you will see, cholesterol. Here it is. It's cholesterol. So the units here. You see here. Those are the 4 fused rings. 3 of them is 6-member cyclic ring, and the other one is 5-member cyclic ring. And then they have this this hydrocarbon group, and 2 methyl groups here. Here it is. 2 methyl groups, 1, and 1 hydroxy group. So this is cholesterol. This is cholesterol. Cholesterol is considered to be steroid. Why? Because it has the basic nucleus of the steroids, or called this steroid skeleton, the 4 fused cyclic rings. Now let's go and look at the cholesterol in some, in some basic details. Cholesterol is manufactured naturally in the human body. It is very important compound, correct, in the cellular membrane, including in myelin and brain and nerve tissues. Cholesterol is manufactured in the liver, and it's also found in the bile salt in the human skin, which can be converted into the D vitamins when the human skin is exposed directly to the sun. So this is just an information about cholesterol. So this is cholesterol really manufactured in the body. Now you will see there is a good cholesterol and bad cholesterol. So cholesterol can have divided in 2 classes: low density lipoprotein, LDL, and high density LDL. The low LDL, low density lipoprotein, those are the called what? Bad cholesterol. Correct? And bad cholesterol, because first of all, they are not soluble, as all the lipid, they are not soluble, and they tend to lead to deposits in the arteries, which block the blood stream in and out the heart, which can cause a stroke. So the blockage of the blood stream in and out the heart this can caused by this low density lipoprotein. However, the high density lipoprotein works the opposite way. It's a good cholesterol. So it's really moving this LDL, low density lipoproteins, away, correct, by emulsifying it and dissolving it, because both of them non-polar, correct. So taking out of the bloodstream and bring it to the liver so the liver can work on this LDL, or just store it to places where it can be used for other things rather than staying in the bloodstream. Correct? So the high density lipoprotein, that's what are desired. Those are good cholesterol. They carries out cholesterol from the body to the liver, where the liver can work on this cholesterol and remove it from the body. So it's really moving the whole LDL out from the bloodstream. Not the whole, but the majority of LDL is pushed away by the HDL, by high density lipoprotein. And if you can see, the cholesterol in human blood is very important, and if it should be less than 200 milligram per deciliter, and if it's above 200 milligram per deciliter, then it can cause stroke. So if you have above 200, then there is possibility that the person will be at health risk. So, and here just a picture how this low density lipoprotein is produced, and you can see. Let me just you don't have to memorize it, but nobody will ask about drawing this, but at least you get the idea how this really works. And this low density, you can see they have a lot of all this. The top are the polar part, the inner part, the non-polar part is inside. You see the chain, all this the head of the polar part, and all this. But this is because it has phospholipids, that's what I said, phospholipids based on the fatty acids. And some of these, the black one, if you look at the black one here, that's cholesterol ester. That's the cholesterol, and it has an ester through it. It's OH. Remember, cholesterol has an OH, so it has an ester, and that's the black one. If you look at the black one, that's estriol ester, and all this very complex, and they are least soluble compared. Least soluble, and they tend to deposit in the artery, blocking the blood stream. Let's look at the high density. It's totally different. You will see a lot of polarity there. So if I look at this, we don't have to memorize it, but you see a lot of it's a methyl tab of structure, and it has a phospholipids, the blue one here, the head, all these blue ones, phospholipids. And this is like a missile. You remember the missile of phospholipids? They can bilayer or bilayer or micelles. So like a micelle, sorry, like a micelle. So this is the high density lipoprotein, which can use to carry out this low density lipoprotein. Let me go back and make it smaller here, like the original one. Now just here show you what's the difference between the bad and the good high density lipoprotein and low density lipoprotein. You will see this is like a circle, looks like a circle here, see here, and this one here is an open, see, no circle, it's an open, okay, like a ball. So the good high density lipoprotein regulates LDL storage and promotes excretion, and it promotes its transfer into the lipids, which can be worked out, correct? And here is the area in the bloodstream, in the arteries. So you'll see this is started depositing, and the area will be smaller and smaller, so the blood will not go through after a while, and that's lead to a stroke. So another type of steroids, we looked at the cholesterol, one type of the steroids, but we have other types. The second type called bile salts, and you see the bile salt is nothing really mysterious about it. This is the structure we found in what? In cholesterol, correct? Almost correct. And here just we added another OH, and this is this one here. Let's look at this. What you can tell me about this? This is a carboxylic acid, amino acids, correct? Carboxylic, this amine group here. That's amino group, and this is carboxylic acid. And if you look at this, and this is here, looks like an imide. If this will be later on, we'll talk about it. That's an imide group. But in general, at the end, we look at the end of this. This is carboxylic acid because it has carboxylate ion there. So this part is this part is polar. Let me just this part is polar, and this part here non-polar part. So you have all this. Here it is. This is non-polar part, and this is polar part. So the bile salts, then you can see they are steroids because they have the same nucleus, correct? The skeleton, the four fused cyclic ring, they are there. So the bile salts are salts because you have an ion of the carboxylate ion, correct? On the top of the fifth, the 5-member ring. So they are, if you look at this, they have 5 or 8 carbon side chain terminating in a carboxylic fatty acid. So they do have carboxylic acid, correct? That's what we said. And an imide group as well. They have several hydroxy group. This is the same like here. They have one extra compared with the cholesterol. And because of these hydroxy groups at different locations, you can figure out different types of bile salts. So what are those bile salts? It turns out bile salts, they are acting as what? And it's very important. They are acting as detergent to dissolve insoluble cholesterols, correct? That's especially, it helps the high density lipoproteins, and the bile salt is helping as well as a detergent, as a solvent, because all of those are non-polar. But remember, this has a polar part, although small, but it has a polar part, this bile salts. So this process called cholesterol absorption. So by bile salts act as a solvent, dissolve insoluble cholesterol, and therefore help in the digestion of the fats and oils by emulsifying them into micelles, which will be then carried out and get rid of. Correct? So what's the function of the bile salt? The bile salt helps the body to dissolve dissolve cholesterol by cholesterol absorption and move it away in a micelle type of structure out of the body. So some bile salts are acting as hormone steroids. So the bile salts can act as hormone steroids. Hormone steroids are produced in the adrenal gland. The liver is producing these types of hormones from fat and carbohydrates and proteins, correct? So they are produced in the adrenal gland. I think is in the top of the kidney, and those steroids, hormone steroids, are produced in the liver as well. As you will see later on, if you study nursing or anything pre-med, the liver is really a manufacturing plant, manufacturing a unit of a lot of stuff for the body, a lot of hormones, a lot of lipids, a lot of stuff is really produced inside the liver itself. So now these steroid hormones are produced in the liver, and they have several functions. They are controlling inflammations in the body. They are controlling in the body the metabolism. They are controlling the immune system. They are controlling the water balance in the body as well. You believe it or not, they are controlling the sexual characteristics in the body and fighting sickness. So you will see some of those. You might be familiar with those. Okay, so let's go and look at the. Let's go and look at the steroid hormones. They are really fat soluble. They are not water soluble. They are fat soluble. So they are non-polar. steroids because they have the fused four rings, correct? They are very similar to cholesterol, but they are not cholesterols, but they are looking close to cholesterol, but they are not cholesterol. They are bile salts. They are really what? Bile salts. And they have the carboxylate ion and the fused ring, four rings. They are fat soluble, and they pass through the cell membrane. And when they pass through the steroid hormones, they go to the cell membrane. They pass the cell membrane, correct? And maybe I can't just read. If you allow me, I will go and explain this one here nicely in this. So those lipids here, if you look, that's what we talked about them. Those the steroid hormones. This is the blood stream, correct? This is all bloodstream here. They can drop out here, out of the bloodstream, and this is one of the cell, body cell here inside. And remember, this is all. This is outside the cell. This is polar. All this polar H2O, correct? This is all of it H2O. Now this inside the cell, correct? And remember, this is the outer wall of the cell, non-polar. It's non-polar. It's not allowing H2O to come in. So non-polar. So the lipid soluble hormone will go through, and then it have a lipid soluble hormone diffuses through the plasma membrane. So the plasma membrane will allow the lipid soluble hormone to go through, correct? Because the plasma membrane is not water soluble, but it is fat soluble. So when this lipid is going through the cell, it will act this. Remember this, the blue one here, the blue one. Our lipid soluble hormone is the yellow circle here, and the blue, this is receptor hormones, and they will make a complex. This complex called receptor hormones complex. So it's enter the plasma membrane, plasma, through the cytoplasm here. This is all the cytoplasm here, all the cytoplasm outside the nucleus, and this is the nucleus, correct? The nucleus is as you see, is protected by phospholipids, bilayer. Remember we talked about the bilayer of the phospholipids. They can make micelles or bilayer, and this is protected by the phospholipids bilayer outside the nucleus. So protected by this. So now the plasma the hormone might be not able to enter this nucleus, but because of the help of the receptor hormone, now they make a complex. They will be allowed to go in and inside the nucleus and attach themselves to what? To DNA of the nucleus. When they attach themselves to the DNA, and then you see hormone binds with the receptor in the cytoplasm, forming a receptor hormone complex. Now, they were successful in making a complex with the receptors. They are now a complex between steroid hormone and the receptor, attaching themselves to DNA, trying to copy it in the process called transcription. Transcription is copying small part of the DNA, not the whole DNA, but part of it. Part of the DNA will be copied in the process called transcription. And this is what's happened, the transcription. The receptor hormone complex enters the nucleus and triggers gene transcription. The gene transcription, genes copying, not all the DNA, gene map, but at least part of it. And they produce something called mRNA, message ribonucleic acid. So this small tiny one here is transcribed, copied from the the mother or the father DNA, correct, whatever you call it, from the parent's DNA. And this now, transcription is done, the copying is done. It's time to get out of the nucleus in the process called translation. Here it is, translation. Translation is when the translation is happening when it's the transcription, the copying is happened, correct? And the hormones coming out with the receptor and attach themselves to the DNA, the parents producing mRNA. This is a copy, message ribonucleic acid, a copy of the genes from the DNA. And now this one here, you can see here, this one here, the blue one, this is mRNA. And attached to the big one is the protein here. See here, that's a protein. All this, when it's attached itself to the protein outside the nucleus, now you have activated these proteins for different functions. So the transcribed mRNA is translated into proteins that alter cell activity. So whatever is copied from the parent's DNA will be then translated or copied into the protein here, and this copying this copying process leads to the activation of these proteins to certain cell activities. So that's really very nice to know how these hormones are acting. And I think we'll get some example of this. If you look at this example, just to tell you, this is the male hormones, correct? And this is the female hormones, correct? So you can see the difference. They are almost identical, except the difference here, the difference between them is this one here. So the difference is, trying to get this one here, yeah. So this one here and this one here is the difference is between them. So this is the testosterone and estrogen. So yes, sometimes you get estrogen or progesterone. So those are male and female hormones. That's a male one here, that's a male one here, and there's a female one here. And then you have another one. You have cortisol and corticosterone. So corticosterone, and you see they look very identical, correct? It's really nothing really different, except the only difference is the OH here. So between this one here and between this one here is the OH. So the OH is the difference between them. Otherwise, it looks very identical. That's a cortisol, that's a corticosterone, correct? So that's cortisol, that's corticosterone. So those are the compound produced inside the body, and you have seen that the liver is one of the manufacturing places for those steroids hormones, correct? And here it is just to give you an example of the corticosteroids. They are produced in they are chemical compounds, of course, produced in the adrenal glands, which is located above the kidney. The corticosteroids increase the blood glucose concentration and facilitate the protection of glycogen in the liver. They help the kidney balancing the electrolytes in the electrolyte concentration and water amount. And this is just an example of the corticosteroids is the cortisol. Let's go up and look at this. This is the cortisol here. This is the cortisol we're speaking about. You can see still the four fuse rings are there, the steroids. And as I said, example, this cortisol helps to minimize the stress increase the blood glucose, and regulate the concentration of fats, carbohydrates, and protein metabolism. Now, however, those are the natural produced ones inside the body themselves. Now, sometimes if they are in low concentration, they have to be given to the patient, to the sick person, externally. So we use the synthesized hormones, steroid hormones. The synthesized steroid hormones are called corticosteroids. Corticosteroids are used to, as I said, for inflammation, fighting asthma, fighting arthritis. But in all this, whatever they are good thing they are doing, the manufactured one and given to the patients, we have a problem of side effects. So what are those side effects? Well, you can see they are making the skin very thin. The body of the patient or the sick person will be susceptible to bruising. They make the blood pressure very high, and the body will be susceptible to infections, and a lot of fat build up around the face, the chest, and the abdomen, thinning the limbs, and osteoporosis, thinning of the bones, maybe leading to the bone fracture, and particularly in the spine, and the fluid retention and diabetes. So it has a lot of side effects. So therefore, you cannot take those out by yourself. They have to be monitored and controlled by a physician. So if somebody is lacking those hormones, it's very dangerous. But taking them by yourself is dangerous as well, because you need advice of a doctor, because if the side effect of them is I mean, you can see is huge. You get a lot of diseases, a lot of problems, blood pressure. You get your bones will be so weak, and you get overweight and diabetes, and you get a lot of stuff if you take them without guidance and advice from a physician. And this here just some synthesized corticosteroids. Corticosteroids are manufactured, synthesized, manufactured, and sold in the pharmacy, correct? And those are here. You can see hydrocortisone, prednisolone, and all those. I mean, all those here. Those corticosteroids, and they should really be used under guidance and advice of a physician. Thank you very, very much for the first part, and we'll come back and talk about the next part soon. Thank you very, very much. Thank you.